So let's do some problems. So let's say we have a wheel with a fixed axle. So this axle can't rotate on its own. It's connected to the larger disc. And the entire setup here has a moment of inertia of 15. And from the center of the wheel out to the edge, that's R1 with a force of 20 newtons. And then for this one, we have a smaller radius and the force is exerted at an angle. And the question is to find alpha. So what we're going to do is we're going to sum our torques. So we're going to do the sum of the torques is equal to I alpha, so this is our net torque, is equal to torque 1 plus torque 2. But when we use our right-hand rule, we see that this torque right here, the first one, is into the page. So let's call that positive. And then our second torque, we can see is going to be out of the page, so that's going to be negative. So when we put our numbers in here, we're going to have I alpha is equal to, and then we're going to have R1, F1, and that's going to be our 20 newtons, and we're going to call that positive, minus, then we have R2, and then we have to look at the component of the force that is perpendicular to the radius. So that's going to give us, we're going to have to use cosine in this case, so that's going to be F2 cos 60. So when we put the numbers in here, we end up with 15 alpha is equal to 20 times 0.2 minus 80 times 0.5 times 0.1. And this comes out to 4, and this comes out to 4, meaning that alpha comes out to 0. So what does that mean? Well, that means that the net torque is 0. So if the object was rotating, it would continue to rotate at the same angular velocity. Or if it was at rest, it would remain at rest. Now, the next part of this question says if F2 is removed, find the angular velocity after 5 seconds. So if we remove F2, so we're going to get rid of this. We only have one torque acting on it. That's going to be R1 cross F1. So let's go ahead and do that. So that's going to be net torque, or we could write it as sum of the torques, the summation symbol. Either way, it's the same thing. And that's going to be I alpha is equal to, and that's going to be torque 1. So we know that that was 15. We now are going to have a new alpha, and it was at 0.2 meters times 20 newtons at right angles, and that gives us an alpha equal to 0.27 radians per second squared. Now, this came out positive because our net torque was positive, which was into the page. So we haven't done this yet, but our change in angular momentum must also be into the page, and we'll do those problems when we get to angular momentum. But the question was, how fast is it going to be going? So we're going to have to do omega final equals omega initial plus alpha t. We're doing rotational kinematics. And we're saying that it started from rest. I didn't write that down, but we'll say it starts from rest. And that's equal to alpha 0.27 radians per second squared for 5 seconds. So how fast will it be going at the end of 5 seconds? It'll be going 1.33 radians per second. This question is usually part of a bigger problem. Typically what you have is a bar of length L and its mass M, and it's connected to a hinge and it swings down. So this whole thing rotates down. And usually the question is, what's its initial angular acceleration, and then they'll ask you how fast is it going when it gets down to the bottom. But to do that part, we need conservation of energy, and we haven't done rotational kinetic energy. So we're just going to do the first part of this question, which is find alpha initial. Well, is there a torque on it? Yes. The force, we're going to say, is acting from the center of mass. So that's our Fg. So our R is only out to L over 2. So the reason that we're saying initial angular acceleration is because as this starts to swing down, the component of force is changing. So it's not a constant torque. We're just finding it at this instant. So to do this, we say net torque is equal to I alpha initial is equal to, and then it's going to be R cross F. Well, what's R? R is L over 2. And what's F? That's Fg, so that's mg. And it's a rod of uniform density. So we say that's 1/3 ml squared times alpha naught is equal to mgl over 2. And then we have our masses cancel out, and one of the L's cancels out. And then we solve and isolate for alpha naught, and we get 3/2 G over L. A fairly straightforward question. Okay, in this problem, we have an axle that's running through here. It's a fixed axle. We have a bar of length 4 meters. It has a mass of 1 kilogram, and we're applying a force perpendicular. So that's R cross F, and it's starting from rest, so it wasn't moving initially, and this force is constant, but it's also perpendicular. So as this rotates, the force turns with it. So this force is constantly angularly accelerating the rod. And the question is, what's the net torque? What's alpha? And after 5 seconds, what's its angular velocity? So for the first question, we can just do net torque equals R cross F. And it's pretty easy because all we have to do is throw those numbers in. But where is this force acting? It's acting from this axis of rotation. So it's not the length of the bar, it's half of the length of the bar. So that's going to be 2 meters times the 200 newtons of force. So what's the net torque? That's just going to be 400 Newton meters. So in part B, we are solving for alpha. So what we can do is say that the net torque, which is R cross F, but remember, it's also equal to I alpha. And that's equal to R cross F. So we know that I, for a bar spinning about its center, is 1/12 ml squared, and that's times alpha, and that's equal to R cross F. So if we put our numbers in, we have 1/12, 1 kilogram was the mass, times 4 meters squared, because remember, and I've had a lot of students ask me this L is, for the moment of inertia, is the entire length of the bar, whereas before we were using half of the distance because that's where the torque was acting from. Okay, so we have 1/12, 1 times 4 meters squared, all times alpha, is equal to our torque that we solved for before, which was our 2 times 200. And when you do the math on that, you get a constant acceleration of 300 radians per second squared. And the last question was, what is its angular velocity after 5 seconds? So this becomes an angular velocity using rotational kinematics problem. It started from rest, so our omega initial is 0. Our omega final is what we're looking for. Our angular acceleration we just solved for, and we know the time is 5 seconds. So all we have to do is do omega final equals omega initial plus alpha t, same as in the last problem. Started from rest, so that's going to be 300 times 5 seconds, or an angular final velocity of 1500 radians per second. This problem is a little bit tricky to understand, to sort of figure out what's going on in the problem. Essentially, you can think of a potter's wheel, and this potter's wheel is spinning, and it's spinning at 5.23 radians per second as it goes along. And then the potter takes a rag, and they push the rag up against the potter's wheel to slow it down. And it takes 6 seconds before it stops. So think about this. The force of the rag is pushing this way, and that's like force normal. It's acting perpendicular to the surface. So what are we going to get as the result? We are going to get a force of friction. And that force of friction is going to be the force that develops our torque that is going to end up angularly accelerating this, in this case negatively, to slow it down. It's a disk, and they give us the moment of inertia, so that's nice, and they give us the radius and also the force of the rag. Now, because they gave us the force of the rag, essentially they've also given us the force normal, because that would be an equal and opposite force pair. The question is to find the coefficient of kinetic friction. It's sliding, so it's kinetic. So the first thing that we need to do is to figure out alpha. And we can do alpha just with omega final equals omega initial plus alpha t. So that would be 0. It comes to rest. It starts out at 5.23 alpha, and then we know it's 6 seconds. So our alpha comes out to a negative 0.87 radians per second squared. The negative is going to be the opposite of the direction of rotation. I should have said we were going to define that as positive. Keep in mind also the friction will be opposite that direction, so this is also going to be negative. Now, to figure out the coefficient of friction, we need to do a net torque equation. So we sum up our torques, which in this case is only going to be 1. Net torque is equal to I alpha, and that's going to be equal to R cross F. And in this case, F is FF. So now we have I alpha, and that's going to be R. And then what's force of friction? Well, it's mu K Fn. So they gave us I, which was 12.5. We know the angular acceleration is negative 0.87 equals the force of friction is going to be negative, so we'll put our negative sign in there. And then we have our 0.5 times the coefficient of friction times 70 newtons for our force normal, and mu k comes out to 0.31 for a value. This is a very common question. We have a disk here, a solid disk, and the solid disk has a string wrapped around it and then a mass that's hanging off of this, and it starts at rest. So you can think about this as the weight is pulling down on this string, and the string is going to apply a force, that's a force of tension, at this radius r, which is going to produce a torque and make this start to spin. And it's a constant force, so we're going to have a constant net torque, which means we're going to have a constant angular acceleration. So that's what we're looking for first, the angular acceleration of the disk. But they also want to know what's the angular, or what's the linear acceleration of the block, which is going to be the tangential acceleration of a point on the rim. And then lastly, what's the tension in the string? So before we go too far with this, the first thing we should do is do a diagram looking at the forces and then also what the torques will be. So the first thing that we have is we have a radius r, and then we have this force of tension 1. Now there is the force of the hinge itself, but if this is our origin, that's not producing any torque, so we can ignore it. So we just have r at Ft, and we'll call this direction positive. So what else is happening here? Well, we have the force on the block. So what forces are acting on the block? Well, we have the equal and opposite force of tension here. So we don't get confused, let's call that force of tension 1 and force of tension 2. And then we have the weight of the block, which we know has to be larger so that there's a net force down and acceleration. So the way to solve for alpha, the best way to do this, is to do it as a system. We'll do everything all at once. We'll treat this as one system. So what we do is we say net torque equals I alpha is equal to, and let's see what we have. Well, we have R cross FT1. So that's going to be FT1. Then we have FT2 acting up, but also at this same radius in the opposite direction. So that's going to be a negative torque. If we wanted to do this properly, we would do the right-hand rule. But we know they're opposite directions, so that's FT2. Plus, then we have FG acting down at radius 2 meters. So that's going to be plus RFG. And that's Fg of the hanging block. These are equal and opposite forces at the same radii, so those cancel out. Now, what's the moment of inertia of the system? Well, that's going to be 1/2 m2, that's the disk, r squared. Why? Because it's a solid disk, and solid disks have a moment of inertia of 1/2 mr squared. Plus the mass. Now, this is a tricky idea. The mass is staying at radius r the whole time. So this force is acting down. It has inertia that is perpendicular to this radius. So as it falls, it's acting like a point particle. It's acting exactly the same as if it was on here and spinning around in a circle. So that's acting as mr squared, but we're going to say m1 because we defined it that way, all times alpha is equal to, and then we just have this right here, which is our R cross mg, and that was m1g. So now we just need to plug some numbers in. So I'm going to bring the alpha out front, and we have 1/2 3 times 0.2 squared plus 0.5 times 0.2 squared, all times alpha is equal to 0.2 times 0.5 times 9.8. And if you work out the numbers, you get an alpha of positive 12.25 radians per second squared. Okay, so that was a lot of work, and we solved for this. So this thing is going to start speeding up. Its angular velocity is going to increase in this direction. And now we have to find the linear acceleration of the block. Well, the linear acceleration of the block is the tangential acceleration out on a point of the rim. So all we have to do that one is just A tangential equals ralpha. So that's just AT equals 0.2 times our 12.25. So our tangential acceleration, which is our linear acceleration in this case, is 2.45 meters per second squared. Also positive, which is down in this case. Okay, for the final question, it says, what's the tension in the string? What's this force of tension? Well, now that we have the linear acceleration, we can use just a net force equation to figure out Ft2. So to do that, we're just going to say this is on the 0.5 kilogram mass only. So that's going to be F net equals ma equals Fg minus Ft2. But what I did in this equation was I made this positive because this is our unknown. This is what we're searching for. So if our unknown, like sort of solving for x, we leave it as positive, even though we know it's negative. So the check of that is to find out if this comes out negative. So we have 0.5. We know the linear acceleration is 2.45. Equals 0.5 times 9.8, and we add our Ft, and as we expected, Ft2, our Ft2 comes out to negative 3.7 newtons, which means that it's acting up in our system. This will be our last problem in the torque video, and it's a fairly difficult problem, but it's basically one more added piece from the last problem. So when we did these things before, back in the forces unit, the pulley did not have any mass or there was no friction, in which case these would accelerate in this direction like that. And the force of tension in this string would be equal to the force of tension in this string over here. But now this 5 kilogram mass is pulling on the pulley, which is also pulling on the 2 kilogram mass. So this force ends up being larger. So the question is, find Ft1 and Ft2. So let's define this as Ft1, and over here we'll call this Ft2. So the first thing that we should do is draw a free body diagram. So on this side, we have Ft1 acting up, and then we have a smaller Fg acting down. We call that Fg1. Why? Because we know it's going to accelerate in this direction, which we'll call positive. So on this side, that's positive. Now, that force of tension is the pulley, the string from the pulley pulling up, but the equal and opposite force is going to be a force down. And so that force of tension is going to be equal to this force of tension. So let's put those both as 1. And then the 5 kilogram mass, that has a force of tension acting up, but it also has a force of gravity acting down that we know is larger. Fg2 is larger than Fg1, but it's accelerating in this direction. So Ft2 is going to be up, and it's going to be less than Fg2, but more than Ft1. So we'll call that Ft2. There's an equal and opposite force acting here. We have the force of tension down on the disk and the force of tension up on the mass. So we, over here on this side of the disk, we have an Ft2. And you can see that we have battling torques, one torque trying to rotate it one direction, another torque trying to rotate it the other, and this torque due to this force is going to win. So the question was to find these forces of tension. But if we do that without the acceleration, we're going to end up with two unknowns. So the way to do this is to start out by solving it as a system and getting the angular acceleration, which can then get us the linear acceleration. So solving as a system, we have our net torque is equal to I alpha, and now we've got a lot of stuff here. Now, most people would shortcut this, but I'll write it all out. We have RFT1 minus RFT1. Now, what are those? Well, that's this force of tension and this force of tension, opposite directions, same radius. Then we have the force of gravity producing torque, and that's going to be down on the left side, so that's negative. So that's RFG1. And then on the other side, we have two forces of tension, both acting at radius r. So that's going to be plus RFT2 minus RFT2. And then finally, we have the force of gravity acting at radius r. So that's going to be plus rfg2. So these two are equal and opposite torques, so they cancel. These two cancel as well. Now we have the moment of inertia of the system, because we're solving for a system here. So we're going to have the moment of inertia of this block, and like in the last problem, you can see that's just going to be m1r squared, plus the moment of inertia of the disk, and they don't tell us it's a solid disk, they just give us the moment of inertia as 5, so we'll leave that as id, plus the second object acting at radius r, so it's acting as a point particle, so that's m2r squared all times alpha, is equal to, now what do we have left here? Well, we have r fg2 minus r fg1. I'm just switching the order there. And now we put our numbers in. So we have 2 times 0.5 squared plus 5 times 0.5 squared, all times alpha, is equal to 0.5 times 5 times 9.8 minus 0.5 times 2 times 9.8. And when you solve that for alpha, you end up with 2.2 radians per second squared. But if we're going to find the force of tension, then we're dealing with this not as net torque, but as net force. So we need the linear acceleration. So we're going to do the same trick that we've done before, which is to say A equals ralpha. So we have A is equal to 0.5 times 2.2, or our linear acceleration, which is also the tangential acceleration, is 1.1 meters per second squared. So we did a lot of work here to be able to find the acceleration. But the reason this is important is because we can now use it here to find the force of tension. That's the missing value. So let's do this on the 2 kilogram block first. So that's going to be F net equals ma. And we have our force of tension 1, which is acting up, and our force of gravity 1, which is acting down. And then we know what acceleration is. It's 2 times 1.1. It's up, so that's positive, is equal to force of tension 1, our unknown, minus 2 times 9.8. And that gives us a force of tension of 21.8 newtons. On the other side, we have the 5 kilogram block. So that's going to be F net equals ma equals fg2. And again, we're going to leave this as positive to let the formula predict what that value is going to be. So ma, this time we have 5 on this side, 1.1. It's also in the positive direction. That's 5 times 9.8 plus ft2, our unknown. And then we do the math and you get negative, as we would predict because it's up, negative 43.5 newtons.